So this machine here is a ripple tank, and I want to show you the connection between wavelength and frequency using this piece of kit. It has a plate of water on the top, and the light shines down from this section through the water, is reflected off the mirror, and then projects onto this surface here. When a ripple sets into motion on the tank, it can be seen on this screen here. At the back we have like a ruler that is set into the water, so that when the ruler presses in, it creates a ripple that goes across the tank. Now, an interesting thing about this is that it has a light that can flash at the same rate as the time period of each oscillation, which means it's possible to observe those waves moving, or well, not moving, stationary. And I'll show you what I mean by that. So here, with the lights off, we can now investigate how this ripple tank can show us some wave behaviour. There's a ruler at the back in the water, and the ruler is capable of jabbing down into the ruler because it's connected to a little motor. So let's get it to do that. You can now see it is jabbing down into the water, producing waves that are moving away from the ruler and across the tank. Now what I can do is I can control the frequency, how often those waves are produced. I can put the frequency down, or I can put the frequency up. And you can see that that has had an effect on the wave produced. But it's hard to see because the waves are in motion. Now, one trick that I have to enable us to see this more clearly is the fact that the light source is a stroboscope. It can flash at the same rate as the ruler hits the water. So every time a wave is produced, a flash of light goes through the apparatus, and to our eyes we see the wave in the same place each time, effectively pausing the progression of the waves. If I press it to synchronise, the light source is now flashing at the same rate as the waves are produced. And so you can see that it's frozen in time, the wave pattern. The waves are still flowing, but what we can see is that the pattern is now stationary. And we can observe the effect of change in the frequency on the wavelength. If we lower the frequency, the wavelength increases. If we raise the frequency, the wavelength decreases. So this is as a result of the fact that the speed at which the waves can move through the water is constant. And so therefore, as a result of the wave equation, if the frequency increases, the wavelength must decrease. That's better. Now, red light has a wavelength of about 700 nanometers, 7 times 10 to the minus 7 meters. And blue light has a wavelength of about 350 nanometers. But other than their wavelength, there is no other difference between these two types of light. They are both transverse waves, disturbances in the electric and magnetic fields of space. They both travel at 3 times 10 to the 8 meters per second. And because they both travel at 3 times 10 to the 8 meters a second, it means that if the blue light has a shorter wavelength than the red light, then the blue light must be higher frequency than the red light. And that is the key difference between these colours. It is not just a case that the wavelengths change, but the frequencies do as a result of the fact that they must always travel at the same speed. Previous example with the ripple tank, we found that because the waves always travelled at the same speed through water, increasing the frequency decreased the wavelength. Here, decreasing the wavelength, as is the case with the blue light, increases the frequency because it is tied to wavelength through the wave equation.